The first thing we'll discuss in this class is cells, internal resistance, how to write KCL, KVL in cases where there are cells, including internal resistance. Fine. Can any of you tell me what exactly happens inside a cell? How does a cell maintain that potential difference? See, there are different types of cells. That's fine. Have you studied electrochemistry or not?
Yes,
Did they not teach you about cell in electrochemistry?
they did, sir.
What kind of cell did you learn about?
Daniel cell, galvanic cell.
What happens in Daniell cell?
Like cell will be there, but only the difference will be the cathodes and anodes. Like the different materials will be used.
What else will be there in the cell? Cathode will be there, anode will be there. What else? Cathode is a rod. Okay. Anode is also a rod. What else will be there in the cell?
Salt bridge.
What did you say?
A salt bridge that connects the electrodes.
Okay. And what is that salt bridge made of?
Copper something.
Okay. Fine. Exact compound I also don't know, but it's called electrolyte. Is it or not? Or is it something else?
Yes, the electrolyte.
Fine. So between the electrodes, there will be an electrolyte, and that is what we will discuss now. These days, there are other kinds of cells also, lithium ion cells and all. Okay, for now, we'll consider the Daniell cell itself. So let's say these are the electrodes, and you know the button side is the positive side of the battery. The flat side is the negative side. Positive side is at a higher potential than the negative side. Okay. Now don't think that positive side means positive potential and negative side means negative potential. Okay. Positive side only represents a higher potential than the other side. Okay. Now what happens? The electrodes, due to their chemical properties, they react with the electrolyte surrounding them. Fine. Now on the right side, you have the positive electrode. What is the positive electrode called? Cathode or anode?
Anodes, sir.
Anode. Okay. Negative electrode, cathode. Fine. So anode, cathode, they react with the electrolyte, and due to that chemical reaction, they develop a potential difference. Like ions get deposited. I don't know the exact mechanism, you should be knowing, but due to deposition of ions or that chemical reaction, the anode electrode, that electrode which is on the positive side, it has positive ions getting deposited on it, and the other electrode has negative ions getting deposited on it. Okay. So, okay, have you heard of something called anode potential, cathode potential? No. Okay, fine. So anyway, actually that is chemistry. But from what I remember, when anode reacts with the electrolyte around it, it gains a certain amount of extra potential than the electrolyte. Okay, so let's take it this way. Assume this reference level is the electrolyte potential. Fine. The anode will be at a slightly higher potential than this. Okay, I think that extra potential is what they call as anode potential. Just a moment. Let me try it properly. If there's an exact definition and you know it, you can tell what is anode potential, what is cathode potential. Okay. So let's say this is anode potential, that blue dot. It's higher than the electrolyte potential. And there is something called cathode potential also. Due to the reaction that the cathode undergoes with the electrolyte, negative ions deposit on it, it will have a fixed, like depending on the reaction, it will have a fixed potential difference between itself and the electrolyte. It will be at a lower potential than the electrolyte. Like this. Okay, the other one let us represent in green. Right? So the green dot is the anode potential, the red dot is the cathode potential, and the difference between those two, okay, this complete potential difference is called terminal voltage of the battery. Okay, that's the potential difference that you actually see across the ends of the battery. So when you connect this battery to a circuit, the potential difference that the battery maintains is the difference between the anode potential and the cathode potential. Now, when there is no current flowing through a battery, through a cell, the entire electrolyte will be at the same potential. So electrolyte potential will be a horizontal line like this. Okay, like what I have drawn in this diagram. All the electrolyte will be at the same potential when no current flows through the battery. Fine. And in that case, when current through the battery is 0, the potential difference that you see across the battery is what we call EMF of the battery or EMF of the cell. Okay, battery is actually a combination of cells, but usually in everyday life we call them as batteries. So I'm getting that word. Let it be. We're talking about cells. Okay. So the potential difference across a cell, or the potential difference between the anode and cathode of a cell when no current flows through it, is what we call as EMF of the cell. Okay. Now, what if there is current flowing through the cell? First case. Current flows out of the positive terminal. Now, can any of you tell me what is the job of a battery in a circuit? What is it supposed to do?
To maintain the potential difference.
Maintain potential difference, and to do that, it pulls electrons from one side and releases them on the other side. Okay. Usually, or in most cases, electrons enter into the positive terminal and they leave from the negative terminal. If electrons are going this way, it means the current is going the other way. Okay, because conventional current is the direction of flow of positive charges. So usually what happens in a circuit when a battery is connected, usually, not always, okay, current flows out of the positive terminal into the negative terminal. But see, current in this case also is flow of electrons. Fine. Now inside the battery, it's not vacuum, there is electrolyte present. When electrons flow inside the battery, will they face any resistance or not? When electrons move through the electrolyte inside the battery, will they come across any resistance, or are they completely free to move? Just tell what you think.
Yes, sir, they will.
There will be resistance because that electrolyte is present. No, it's not vacuum. It's not empty space that the electron moves freely without like colliding with any obstacles. Electrons will will undergo collisions inside the battery also. So that resistance experienced by electrons when they move through the battery or through the cell is what we call as internal resistance of a cell. Any real cell will have some internal resistance. Okay, so you can think of it this way. You can imagine a resistance being present inside the cell. Let its magnitude be R. Okay. So hope you all understood what internal resistance means. Basically, it's the opposition to the flow of electrons, or it's basically the obstacles which an electron will have to come across when flowing through the battery, inside the battery, moving inside the battery. Okay. Now let's say current is flowing to the right. Now battery uses chemical energy and it drives current this way. When current is flowing to the right, you consider this internal resistance. Let this point, let's call this point as X and this point as Y. Current is flowing from X to Y. Okay. Then tell me, if current is I and that resistance is small r, how much is the potential difference across this resistance inside the cell? Current is I, resistance is R. How much is the potential difference?
I into R.
IR. Okay. So there will be a potential difference of IR. Okay. Across that internal resistance. And where is the internal resistance? It is present in the electrolyte. Okay. The electrolyte itself offers the internal resistance. That means potential difference across the electrolyte is now IR. Okay. When no current flows through the cell, the entire electrolyte will be at the same potential. There won't be any potential difference between 2 points in that electrolyte. But now, when current flows through the cell, there will be a potential difference across it. Okay. So it will create some difference to how the how the battery functions. Okay. Now see, when no current flows through it, this was the situation. All the electrolyte was at one potential. This is the potential of the positive terminal. This is the potential of the negative terminal. Their difference is the potential difference that you see across the cell. We call that as EMF of the cell. Now, when there is potential difference across the electrolyte itself, the situation will be different. Now, how did we assume the current to be flowing? We assumed current to be flowing normally through the cell. Normally means out of the positive terminal. Out of the positive terminal is outside. Inside the cell, current is going from negative side to the positive side. Now you may ask, how can current go from negative side to positive side? The chemical energy is used to drive current that way. Current naturally flows from high potential to low potential, but inside the cell, the reverse will be happening. Chemical energy forces current that way. Okay. Okay, now you all look at this diagram and tell me, if current is flowing from X to Y, which end should be at higher potential? Like the points X and Y, among the points X and Y, which should be at higher potential? Current is flowing from X to Y, then should X be at higher potential or Y be at higher potential?
X.
X should be at higher potential. So let's consider this electrolyte potential. Which was flat, means which was uniform when no current flowed through the battery. But when current flows through the battery, this is the end X and this is the end Y. When current flows normally through the battery, X will be at higher potential, Y will be at lower potential. So in that case, what happens? This is what happens inside the electrolyte. there will be a potential difference across its ends, you can say, across the ends of the electrolyte. Okay. Now within the electrolyte, there has been some potential difference created, and the chemical reaction between the cathode and the electrolyte ensures that the cathode is at a lower potential than the electrolyte. So that cathode potential has to be maintained. So that will be there. And the reaction between the anode and the electrolyte ensures that the anode is at a higher potential than the electrolyte on the other side. So anode potential also will be maintained. But now observe the difference between the potential of the anode and the potential of the cathode. It's only this much. Earlier, when the entire electrolyte was at one potential, when the entire electrolyte is at one potential, you had greater potential difference between the anode and the cathode. Okay, we call that as EMF. Now, when current flows normally through the cell, okay, when current flows normally across the electrolyte itself, you'll have a fall in potential. Okay, so from X to Y, potential decreases a little bit. Again, at the anode, it increases. But now you look at the potential difference, effective potential difference between the anode and the cathode. Is it greater than EMF of the cell or less than EMF of the cell? I'm asking you to compare this delta V to this EMF. Is delta V greater than the EMF or less than the EMF? Just see and tell. Okay,
Less.
it's clearly less than the EMF. Fine. By what amount is it less? Like this fall in potential across the electrolyte, how much was that? What was the potential difference across the ends of the electrolyte?
I into small r.
I into small r. Okay. Had that fall not been there, the total potential difference between the anode and the cathode is the EMF of the cell E. But due to that fall, it now decreases by IR. So the potential difference across the terminals of the battery now is E minus IR. It won't maintain a potential difference equal to its EMF when current flows through the cell. Okay. We took the case of current flowing out of the positive terminal, means outside the battery, it goes out of the positive terminal. Okay, so we call it as normal flow of current through the battery. So for normal flow of current, this is what happens. Inside the battery, there will be a fall in potential across the electrolyte when you go from X to Y, negative terminal to positive terminal. So the reaction happening at the cathode ensures that the cathode is at a lower potential than the electrolyte. That will always be there, whether current flows or not. The reaction happening at the anode ensures that the anode has some extra potential compared to the electrolyte. That will also be there. It's fixed. Okay. So cathode reaction ensures there's a potential difference between X and the cathode. Cathode will be at a lower potential than X. Anode reaction ensures there's a potential difference between Y and the anode. Anode will be at higher potential than Y. Okay. So normally when current doesn't flow through the cell, entire electrolyte is at the same potential. This is X, this is Y. There's no potential difference between them. At the cathode, the potential is less than X. At the anode, the potential is more than Y. This is cathode potential. This is anode potential. And the total potential difference across the cell is what you call as EMF. But when current flows normally through the cell, the electrolyte won't remain at fixed potential. Okay, it will have a potential difference. And this is what happens. As you move from X to Y, there will be a fall in potential within the electrolyte. Okay. Now, cathode potential is still the same. This one. Anode potential is also still the same. This one. But because of the fall through the electrolyte, okay, fall within the electrolyte, there's an overall decrease in the potential difference, and the potential difference now becomes E minus IR. Okay. Now I think you yourself can tell what will happen when current flows in reverse. That is possible. Current can flow in the reverse direction also through a cell. If there are stronger cells or stronger sources of EMF in the circuit, they can force current to flow in the opposite direction. And also in daily life, when batteries are getting charged, that is what happens. Okay, you connect it to the power source. The power source EMF is 240 volts, 220 to 240 volts. It will be the actual cell that is there inside. Its terminal voltage would have decreased. Like your mobile phone itself, you take, the longer you use it, the strength of its battery decreases, right? So what happens while charging is, okay, wait, its terminal voltage won't decrease. Fine, let's not get into the details. Its terminal voltage will be less than 240 volt. Okay, the battery that you have in your mobile phones, it won't be 240 volt. So while charging, what will happen? The voltage of the power socket, which is 240, will drive current in the reverse direction through the cell in your mobile phone. Okay, and that is how it gets charged. So you all tell me directly, if current flows in the reverse direction through the cell, within the electrolyte, which point will be at higher potential, X or Y?
Y, sir.
Y will be at higher potential, X will be at lower potential. Then the diagram will change like this. Okay, just a moment, I'll copy paste this. We'll keep this aside. This is anode potential. That means the extra potential that the anode has compared to the electrolyte. Now, within the electrolyte from X to Y, the potential has to increase. Y will be at a higher potential. Okay. And how much is this increase? IR. And the anode will have extra potential compared to Y. Now you look at the total potential difference between the anode and the cathode. It is clearly more than the EMF of the cell. Okay. And how much more is it? There's an extra IR. So when current flows in the reverse direction, okay, that is when current flows into the positive terminal of the battery, okay, then the terminal voltage, that is the actual potential difference that you see across the battery, will be more than its EMF. Okay, it will be E plus IR. Okay, hope the idea is clear to all of you. Now the chemistry part you don't need here in physics. Just remember, when current flows normally through the cell, potential difference across its ends, which is what we call terminal voltage. Ultimately, the circuit receives the terminal voltage. Okay, when current flows normally through the cell, the terminal voltage will be less than the EMF of the cell. Okay, so it effectively functions like a battery of lower potential. Okay, and if current flows in reverse direction somehow, current flows in the reverse direction, that is from, okay, that is into the positive terminal of the battery, then the actual voltage that you see across the battery, that's the terminal voltage, will be more than the EMF of the cell. Okay, and to find out how much exactly it is more or less, you need to know how much current flows through it and what is its internal resistance. Okay, let's solve questions based on this. See, you all know the symbol for a cell, right? Positive terminal, negative terminal. If it is only like this, then it's an ideal cell. Now a real cell has electrolyte inside it. It offers resistance to electrons. Okay, so a real cell will be represented this way. You can consider it as an ideal cell combined with some resistance. And these two have to be together. You can't draw any other resistance in between or put a capacitor in between. Okay, because all this is inside the cell. So you can simply treat it as an ideal cell along with a small resistance in series. Okay, how does it work? Assume this is EMF, this is internal resistance. Now if current flows normally, let's say I, then the potential difference across these 2 points, let's call this as A and this as B. Simple KVL will tell you that it is not KVL kind of potential calculation will tell you it is E minus IR. If current flows in the opposite direction, it will be E plus IR. Okay. So suppose there is a cell of EMF E internal resistance R connected with an external resistance capital R. A basic case. Okay. Write the expression for current flowing in this. Write the expression for terminal voltage across the cell. And then write the expression for power dissipated by the external resistance. Power dissipated by, let's say, capital R. Do this quickly, all of you. Okay, Anugrah, how much is the current? What is the expression for current?
Epsilon by R plus R.
Okay, E divided by R plus R. See, you can apply KVL if you want to calculate the current. Otherwise, you can see that there's only one extra resistance present. So capital R and small r are in series. So the effective resistance of this circuit becomes R plus R and effective voltage is E. So you can write the current as E divided by R plus R. Okay. Yash, is the current flowing normally through the cell or is it in the opposite direction? Normally, okay. There's only one source of EMF in this circuit. So it will drive the current this way. That, okay, for this cell, this is the positive terminal and this is the negative terminal. Current is flowing out of the positive terminal, so it is normal flow. Okay. Shashank, tell me, what is the terminal voltage across the cell?
Epsilon minus IR.
E minus IR, you substitute that value of R. Terminal voltage is the actual voltage that you see across the terminals of the cell, across the ends of the cell. Okay. So from here to here, it is E, but across the resistance, there is a potential difference IR. And since current is flowing in the normal direction, current is flowing normally, it will be E minus IR. So it becomes E minus I is E divided by R plus R. into small r. Okay. Simplify it. You get it as E into R, capital R plus small r, minus E into small r divided by R plus R. Small r gets cancelled. You get it as E capital R by R plus R. That's the terminal voltage that you see across the cell. Okay. It is less than its EMF as expected. Next, power dissipated by the resistance capital R. Isha, how to calculate power dissipated by a resistor? Okay. Yashmit, how to calculate power dissipated by a resistor? No response. Anyone else?
V square by R.
You can use V square by R. But for that, you will have to find out V. That's the potential difference across this resistance. Do we know that?
Yes.
We know. Okay. See, this cell is connected across that resistance only, no? So whatever is the terminal voltage, that's the potential difference between X and Y, the same is the voltage across the resistance because it is directly connected there. Okay. And we have already calculated that. So yeah, you can use V square by R. You can use I square into R also. Okay. So power dissipated by the resistor, I square into capital R. Okay, these things you need to be careful about. Small r is the resistance inside the cell, internal resistance. Capital R is the external resistance. I is E by R plus R, so I square becomes E by R plus E square by R plus R whole square multiplied with capital R. Okay, fine. Now, some of you may have studied this already. There's something called maximum power dissipation theorem. Whenever current passes through a resistance, heat will be released. Okay, and the rate at which heat is released is what we call as power dissipated. Okay, release is dissipation. Fine. Rate of release is power. Okay. Power dissipated. Fine. Now tell me, the power dissipated here by the external resistance, clearly it depends on R, capital R. Fine. Now, using this formula itself, you tell me, if capital R tends to 0, how much is the power dissipated by capital R? Or what does the power dissipated by capital R tend to become?
Zero, sir.
How can you say it will be 0? Okay, fine. Easy only. Numerator becomes 0. Denominator is non-zero, so the whole thing is 0. Okay. So if the external resistance tends to 0, then there will be no power dissipated by it. Fine. That's the first case. Next case. If external resistance is too large, tending to infinity, then how much is the power dissipated by it? Anyone?
Infinite.
How do you
Tending to
just
be-
tending to infinity? You're saying infinity. You're saying. How do you justify that? There is an R in the numerator, but there's an R in the denominator also, no? How can you say that if R is very large, the answer will tend to infinity?
Sir, if R tends to infinity, then current won't flow through the circuit.
Okay, if external resistance becomes infinite, see, it is just tending to infinity, no? So current will be tending to 0. But power depends on both of them. Power is I square R. If you talk in terms of current and resistance, it is I square R. R is tending to infinity, current is tending to 0, but their product could still be finite. Anyway, it's just simple mathematics here. Listen, all of you. Power is E square capital R divided by capital R plus small r whole square. There is capital R in the numerator and also in the denominator. That is why we are not able to tell what exactly happens to it. So if you want to comment on what exactly happens to it, you should ensure there is only one capital R, not two. Okay? Or you have to write it in a different way. Send this to the denominator. It becomes E square by capital R plus small r whole square divided by R. That is E square divided by. Now that capital R, which is in the denominator of the denominator, I'll send it into the square. You can write it this way: R plus R divided by root R whole square. So that becomes E square divided by R by root R is root R, root capital R, plus small r by root capital R whole square. Now we know capital R is tending to infinity. If capital R tends to infinity, this first term becomes 0. Not first term, that second term becomes 0. But this becomes infinite. And infinity plus 0 is still infinity. When you square it, the entire denominator will be tending to infinity. And then the power dissipated will be tending to 0. Okay. That is one way to answer. Another way to answer, capital R is tending to infinity means capital R is much greater than small r, right? If capital R is much greater than small r, then the power dissipated by it can be written as E square R divided by, in the denominator, small r can be ignored. If you ignore small r, then it is just capital R squared. And cancel. The power dissipated tends to E square by capital R when capital R is very large. And if this tends to infinity, the whole thing becomes 0. That way also you can tell. Okay. See, this is also an interesting observation. This formula, when capital R is much larger than small r, the power dissipation tends to E square by capital R. What is interesting here is if capital R is very large compared to small r can be ignored altogether. It's like there is only one resistance capital R and there is an ideal cell of EMF E. In this case, you know power dissipated will be E square by R, and that is what we see here. Okay, so it's like that small resistance doesn't matter, internal resistance doesn't matter in that case. Okay. Now when capital R is too small, when external resistance tends to 0, power dissipated by it tends to 0. When external resistance is too large also, power dissipated by it tends to 0. But when external resistance is a finite value, not 0, not infinity, but some non-zero finite value, this will be a non-zero value. The power dissipated will be non-zero finite value. So for 0 external resistance, power is 0. For infinite external resistance, power is 0. But in between it is non-zero, means it should follow a nature somewhat like this. On the x-axis, let's say you have external resistance. On the y-axis, you have power dissipated by the external resistance. When external resistance is 0, the power dissipated is 0. And as it tends to infinity, the power again tends to 0. Means somewhere it should peak. Okay. So it should be somewhat like this. And then tend to 0. So there will be some value of external resistance for which the power it dissipates is maximum. Okay, this is what is the maximum power dissipation theorem. And okay, if you know it already, you tell me how much should be the external resistance for which power dissipated is maximum?
It should be equal to the internal resistance.
Should be equal to the internal resistance. When external resistance is equal to internal resistance, you'll see that it dissipates maximum power. How do we prove it? power is E square capital R divided by capital R plus small r whole square. Now we want to find out, Anugrah, I'll answer your question in a while. We want to find out the resistance capital R for which power will be maximum. So capital R will be treated as a variable. Accordingly, power will also be a variable. And we want power to be maximum. Power is maximum means derivative of power with respect to resistance should be 0. That's all. You differentiate this function and you equate it to 0, and then you solve for R. You will see that capital R should be equal to small r. Only then that derivative is going to be 0. So if capital R is small r, the power dissipated by it will be maximum. Okay. Now the question, the doubt I got is, according to the formula V square by R, very low resistance means very high power dissipation. Correct? How? Because high resistance, more heat will be released. But low resistance, how is it releasing more heat? Okay. See, power dissipated. Of course, you need resistance to dissipate power. Electrons should undergo collisions. That is when heat will be released. But how much heat will be released when an electron undergoes a collision depends on how fast the electron is moving before undergoing that collision. No, a slow moving electron, if it undergoes a collision, it will release a little bit of heat only. But when a fast moving electron undergoes the same collision, it will release more heat because it had more energy due to the drift. Okay, so power depends on resistance. It also depends on how fast the electrons are moving. It depends on current. Okay, and the actual formula is I square R. From this, it changes to V square by R. Fine. So simply because resistance is low doesn't mean power is high, or power is high or power is low. It depends on the voltage that you are applying also. It actually depends on the current. Current can be calculated from the voltage. Is your doubt clarified?
Yes, sir.
Okay. Fine. Okay, so basically whenever there is a cell along with internal resistance, you treat it as an ideal cell with some resistance in series. That's all. Next, let us discuss combination of cells in series. Let's say there's one cell like this, EMF E1, resistance, internal resistance R1. In series with another cell, EMF E2, internal resistance R2. You can take any number of cells like this. No junctions in between, then you can call it as a series connection. Okay. Tell me, now this is a combination, right? What we want to do is we want to replace this combination with a single cell, which will behave in the same manner as this combination would behave. We call its EMF as effective EMF. We call its resistance as effective internal resistance. Okay. Suppose no current passes through this combination. Let's mark these points. Let's say there is no current. Then how much is the potential difference between A and B? When there's no current, what is the potential difference across the first cell?
Zero.
Why? Why will a cell not have potential difference?
It will be E, sir.
It will be equal to its EMF. Okay. You don't have to connect a cell to anything. Simply it will be maintaining potential difference. That is the EMF. Okay, so from here to here, the potential difference is E1. And when no current flows, the potential difference across the second cell will be E2. And you can see how they are connected. Okay, negative, positive, and then negative, positive. So from here to here, it increases. Again, from here to here, it increases further. So the total potential difference across the ends, that is from A to C, will be E1 plus E2. Okay, so this effective EMF has to be E1 plus E2. Okay, suppose current flows through this combination. If current flows, then across the first cell, it will be E1 minus, let's say normal, let's assume normal flow of current. It will be E1 minus I R1. And across this, it will be E2 minus I R2. Then the total potential difference becomes E1 minus IR1 plus E2 minus IR2. That is E1 plus E2 minus I into R1 plus R2. So this is like the effective resistance. Just like series resistors, you can add them. So R effective becomes R1 plus R2. Okay. We'll also discuss the case when one of them is connected in reverse. We'll come to that. But from this, it seems like the effective EMF is E1 plus E2. You just have to add the EMFs. The effective resistance is R1 plus R2. You just have to add the internal resistances. Okay. If there is a third one, you add the third one also. Now let's consider a slightly different case. One cell having its positive terminal to the left and some internal resistance. Another cell having its positive terminal to the right and some internal resistance. Let's say current is flowing to the left. Fine. Or first we'll take without current, what is the EMF and all. Let's say E1 is greater than E2. And let's also mark the points A, B, and C. Okay. Quickly tell me, when there's no current, what is the potential difference between A and B? When there's no current.
E1.
It will be the EMF of the first cell itself, E1. And when there's no current, potential difference between these two will be E2, but it's in the opposite direction. So effectively what is happening here, across AB, it's like this. A is at higher potential, B is at lower potential. Between B and C, it's like this. B is at low potential, C is at higher potential. Okay. So it is kind of like minus E2. Or if you take that as E2, then this should be taken as minus. Let it be. So imagine going from A to B. If you go from A to B, the potential decreases. A to B, the potential decreases by E1. And then from B to C, the potential increases by E2. So if you go from A to C, you can effectively say that the potential decreases by E1 minus E2. See, decreases by E1, I'm writing as it is. The second case, increases by E2, can be taken as decreases by minus E2. So what is the total decrease? E1 minus E2. Therefore, if you replace them with a single cell, the decrease as you go from this side to that side should be E1 minus E2. So that's the effective EMF now. we still have to find out the effective internal resistance. Okay. Let us now assume some current flows through this combination. Let's say current flows to the left. Now, for the first cell that is between A and B, this is normal flow of current. So here the potential difference will be E1 minus IR1. For the second cell, this current is reverse flow of current. Then it will be E2 plus IR2. Okay. Now go from A to B, then to C. The total decrease in potential will be, first it decreases by E1 minus IR1 across the first cell. Then it decreases by minus of E2 plus IR2 across the second cell. Then it is effectively like E1 minus E2 minus I into R1 plus R2 itself. Okay. Now we know this was the effective internal effective EMF. Then this part should be the effective internal resistance. So we once again see that effective internal resistance is the sum of individual internal resistances. So it doesn't matter whether the cells are connected with same polarity, like in this case, or with opposite polarity. There could be any number of cells in that branch. To find the effective EMF, polarity matters. But for internal resistance in a series combination of cells, polarity does not matter. Okay. So just a moment. Okay. So when cells are connected in series, the effective EMF of the combination becomes E1 plus E2 plus so on up to En. I'm putting a star here. Can any of you tell me what is the condition? Why did I keep a star here? When is this correct? When can you simply add all the EMFs?
When opposite polarities are connected.
See, okay, Anugraha, you don't say opposite polarities are connected. No, no. When cells are
Positive and
connected this way, just a moment. Opposite terminals are connected, but you don't say opposite polarities are connected. Just a moment. When cells are connected like this, placed next to each other this way, you say they are connected with same polarity, not with opposite polarity. Okay, opposite poles or opposite terminals may be connected, but it's the same polarity. They are all arranged with the same polarity is what we say.
Sir, I meant terminals only.
I understood, but okay. Anyway, you get the point. So these are all arranged with same polarity. In that case, you will add all the EMFs. But if any one cell is reversed in polarity, you will have to subtract its EMF. And you see, this is a positive terminal, this is a negative terminal. Then for the effective cell, that side will be positive, this side will be negative. You can't draw it in reverse. Okay. You calculate the effective EMF, but you write the effective cell in reverse, then the whole thing will go wrong. Okay. That polarity also you have to keep in mind. Okay. Next, cells in parallel. Suppose there's a combination of two cells like this. They're connected in parallel, and for parallel combination, junctions don't matter. There may be junctions, may not be junctions. First, when no current flows here or here, it means all the current. See, there are two cells here, right? They will definitely drive current. There's a closed loop also. Fine. E1 will try to make current flow this way. E2 will try to make current flow this way. Some current may leak out, some current may come in. We don't know. Okay. But if there's no current in the wire connected to this combination, then all the current will be flowing inside this loop itself. Okay. Now this is the effective cell. Inside that there will be current. I mean, there may be current. If E1, E2 are different, there may be current inside it. There can be. Now you apply KVL there and you find out the potential difference between this and this. That will be the effective EMF. Because potential difference across the combination, when there is no current flowing into the combination, this current is 0. Internally, there will be current in that combination, but from outside, there's no current. In that situation, whatever potential difference is maintained is what you call as EMF. Okay. Next, you connect this to an external resistance. Then there will be some current from outside also. And then again, you apply KVL, you do E effective minus IR, you will get the effective internal resistance. Okay. It's a lengthy procedure. We are not going to do it. Okay. But when cells are connected in parallel, okay, you will find that the effective resistance can be calculated like how you calculate effective resistance in parallel. So whatever internal resistances are there for all the cells that are in parallel, okay, assume those resistors are in parallel and find out the effective resistance. This will give you the effective internal resistance of the combination of cells. Next thing you need is the effective EMF. For effective EMF, you get a formula like this. E effective divided by R effective becomes equal to E1 by R1 plus E2 by R2 plus so on En by Rn. Again, I put a star here. This is provided the entire parallel combination has the same polarity. Like all of them have the positives on the left side or all of them have the positives on the right side, then you can use this formula. But if any of the cells is connected with reverse polarity, again, you'll have to use a minus sign for its EMF. Okay. So remember, in parallel combination, you can't tell the effective EMF directly. You need to know the effective resistance first. Only then you can tell the effective EMF. Okay. Proof will be lengthy and time taking. It's not necessary also. That's why I'm not discussing. Or maybe in worksheet I'll give you, you can derive it on your own. So remember, in series, the effective EMF is E1 plus E2, so on. Again, star. If any battery is connected with reverse polarity, you'll have to subtract its EMF. Resistance is R1 plus R2, so on. Next, in parallel, you find out the effective resistance first, and the resistance formula doesn't have any condition. Irrespective of whether batteries are connected with same polarity or reverse polarity, resistance is always calculated like this. And then you calculate the EMF. E by R is equal to E1 by R1 plus E2 by R2, so on. Okay. I'll have to stop today's class here.